In today's lesson, let us look at motion in an inclined plane. Imagine an object placed on a slopy surface, just like the object we have here, okay? Now, this object will eventually slide down this plane as such, all right? Okay, let us return our object. Now, the rate at which the object slides down the surface depends on how slopy the surface is, right? That is, if we tilt or we tend to bend this surface, okay, we bend it further like so, all right, or deeper, okay. The rate at which this object will slide on the surface will actually depend on how slopy the surface is, right? And so, in physics, a slopy surface is simply called an inclined plane. But have you observed that objects accelerate down inclined planes like so? You can see the way the object accelerates down this inclined plane, right? Now, why do objects accelerate, that is, gain speed down an inclined plane or surface? Why? Well, this is because of forces that are not balanced. What do I mean by this? Well, an object is said to be acted upon by an unbalanced force only when there is an individual force that is not being balanced by a force of equal magnitude and in the opposite direction, as normally two forces equal in magnitude and in opposite direction would balance each other, right? Now, in order to understand this kind of motion in an inclined plane, it is important to analyze the forces acting on object on the inclined plane, all right? There are always at least two forces acting on any object positioned on an inclined plane. And so in this case, we have two forces that are acting on this object on this plane. Now, these forces are force of gravity, which is known as the weight, acting in a downward direction, right? So we have the force of gravity acting downward like so. Right now, they said the force of gravity is seen as the weight W. Okay. Now, from our previous lecture, we found that weight is equal the mass of the body times the acceleration due to gravity G acting on that body, which is mass times G. And so this is our weight, all right. And then we have another force called the normal force. But first, what is this normal force? This is the support force exerted on an object that is in contact with another stable object. Okay? Now, this force acts in the direction perpendicular to the surface, like this, alright? So this is our normal force. Let's use Fn to represent the normal force, alright? Okay, now the reason we are having a line and an arrow at its tip, remember what we said about vectors, right? Vectors can be represented with lines and arrow at its tip. The line showing its magnitude, that is the size, and the arrow showing that it has a direction, right? Okay, so this shows that this quantity that we're dealing with, which is force, is actually a vector quantity, right? Now, in fact, when we talk about normal force, normal simply means perpendicular, okay? Again, in this type of motion, our net force, which is written like this, cannot just be determined easily as we did earlier, okay? Because the two or more forces, as the case may be, is not directed in opposite directions, as we have in the case of a body being pulled by an upward force and also being pulled back by its weight in the opposite direction, that is, downwards. But do not fret. We shall see that solving for motions in an inclined plane is also very easy. Thus, the process of analyzing the forces acting upon objects on an inclined plane will involve resolving the gravitational force which is seen as the weight W here, into two components of force. Now, so one will be directed parallel to the inclined plane, like this, okay? So we'll say this is F parallel, let's say FP, alright? And the other directed perpendicular to the inclined surface, like this, alright? And so we have directed perpendicular, okay, to the inclined surface. So let's call this, we can call this, remember now, we said the normal force is perpendicular, right, to the inclined plane, alright? This other component of force, which is the perpendicular component now, is also seen to be perpendicular to the inclined surface, right? And so we can still say, we can either use F perpendicular, or we can simply still say F normal. Alright, that's normal force. You can also say use Fn to represent this. Okay? Now, an interesting thing to know here is that the perpendicular component of the force of gravity is directed opposite the normal force. As you can see here, right? You can see that the normal force, alright, and the perpendicular force, they are both opposite each other, right? And as such, balances the normal force. That is, this perpendicular component of the force of gravity is seen to balance the normal force, while the parallel component of the force of gravity is not balanced by any force at all, and therefore cause the object to accelerate down the inclined plane. Now, you can see that this force here is not balanced at all by any other force, and so because of this, our object, which is a stone in this case, is going to slide down again down the plane, because this parallel force is not balanced, unlike the normal force, which is balanced by the perpendicular force, okay, of the force of gravity. All right, let's return our stone back. Okay, now this parallel component of the force of gravity is now the net force, like we said earlier when we mentioned the net force. So we have this to equal the net force, all right? Parallel. Okay. So we have this. Isn't this quite revealing? Though, in the presence of friction or other forces, say applied force or tensional force, the frictional force, which is seen as the opposing force, must be considered when determining the net force, okay? So, when we are assuming friction is present, let us indicate this, okay? Now, which is the opposing force, okay? Now, we indicate it like so. Okay, so this becomes our F friction, okay? And so it must be considered when determining the net force, okay, which is the sum of the individual forces acting on the object positioned on that inclined plane. All right? Okay. And so put this in mind, that the task of determining the magnitude, that is the size of the two components of the force of gravity, is a mere manner of using equations. Now, let us show how the parallel component of the force and the perpendicular component of the force of gravity can be gotten, okay, using mere equations, all right? If you look closely at what we have on the screen, okay, let us ignore frictional force right now because we are not considering it, okay? Now, if we look at what we have on the screen here, how do we get our parallel component and our perpendicular component, that is this component Fn and Fp? All right, simple. Follow me closely. Now, if we start by completing this triangle that we have here, okay, and okay, let us put this here to allow us. This is still W, all right? Call mg. Okay, now we can as well write this. Recall we've gotten our Fn to be perpendicular to the inclined surface, right? Now, our parallel components can as well be drawn to this side, okay? This is the same thing as our parallel. As you can see, it is still parallel to the inclined surface, whether it is down or above, all right? And so now, when you look at these two triangles, okay, two triangles that we have here, the smaller one and the bigger one, you see that they are a bit similar with each other, right? Now, this is making an angle 90 already, okay, with the horizontal. And as well, our resolved components, okay, is also making an angle. You can see from here, which is the Fn, which is the perpendicular force, is also making an angle 90 with the parallel force. Okay, so we have this to be angle 90 as well. Okay, now what is the next thing we do? Consider the angle theta. Okay, but we cannot assume that theta, since theta is here, that theta will be here too. Okay, we can't assume this. No, what we do is to look at the triangles carefully and know how or where we put our theta, if we are going to actually put our theta here or here. Okay, if we say, let us assume now we're doing this to get the position for the angle theta. Okay, now let us assume drawing this again on this other side to enable us get what we need easier. Okay, so let us try and reproduce this, okay, to enable us get where our angle theta is supposed to be. Okay, if it is going to actually be, if it's going to be here or here, all right? So we just cannot assume the position of the theta, so we have to solve for it. Okay, now let us redraw what we have here on another side of our page, okay, so it doesn't confuse us. Okay, so this is our inclined plane. Okay, now this is the angle it is making with the inclined plane, which here is theta. Okay, theta degree. All right, now this is our weight acting downwards, okay, on this plane, on the object rather, which is W. Okay, then we have the component of the weight, so we have this. Okay, so extending from here, okay, which is our normal force, which we denoted as our normal force Fn, or perpendicular force. Okay, and then when we connect it here, that is this, we have our parallel force, right? Okay, so let me remove this W here so it doesn't interrupt. Okay, and put it here, because this is the line indicating the weight. Okay, so now what do we see here? All right, now let's assume that this theta here, okay, let's assume that theta here is 30 degrees. So let us erase it here and put 30 degrees. Okay, now let's say theta here is 30 degrees. Okay, now we're doing this to get the position of theta. All right, now you can see that the weight, that is the line indicating the weight, is making an angle 90 degrees with the horizontal plane, right? With this plane right here. And so this is 90 degrees. And so from our basic knowledge in mathematics, the sum of angle in a triangle, right, equals 180. And so we have 30, let's say 30 degrees plus 90 degrees equal 180. Right? Okay. But we have another angle here that we do not know. So let's put it as x. So let's rewrite this 30 degree plus 90 degree plus x. Alright? So we have 180 degree here. So now 90 plus 30 will give us 120, right? Plus x equals 180 degree. It's just for indication. Now, so we have x equals 180 degree minus 120 degree. So therefore, s becomes 60 degree, right? So this x here becomes 60 degrees. You can see that here already is 90 degree, right? It is making an angle 90 degree already to the horizontal, right? And so what will be this point? Recall in your basic knowledge in physics, okay? In mathematics rather. Now, the sum of angles at a point will also give you 180, right? So if you have 60 degree again, let's say this angle, let's call it x again, plus x plus 90, okay, equal 180 degree, okay? So we have 150 degree plus x equal 180 degree, right? So we have this, when we do this, we have this to be 180 degree minus 150 degree. So this gives us 30 degree, okay? So you can see now that our x here is giving us 30 degree as well. And you can see that we can say that this angle is this angle. Our angle theta, which is this, on this smaller triangle, is placed here, right? From the explanation we made with this triangle that we drew aside, okay? So with this, we can get our perpendicular force, okay? Or our normal force, and we can also get our parallel force, okay? So now, how do we do this? Again, let us draw out this smaller triangle, okay? So if we do that, we have, let's say, using the same color so we don't confuse ourselves. So we have this, okay? Okay? And we have the same thing here, okay? Now this is our FP and this is our FN, okay? And this is our W, which is the weight. Recall, remember, do not forget. So this is our W. It's supposed to be our inclined plane, alright? And so we found out that our theta here is placed at that point. Okay, now how do we get our normal force and our parallel force? Easy. Now, do you remember this is angle 90, okay? Now, from our knowledge of SOHCAHTOA, okay? SOHCAHTOA, alright? We can easily get the angle theta, alright? Now, if you look closely, to get our angle theta, okay, we can use sine. Let us see if we use sine, if it's going to give us what we want. Now, we can get our angle theta as well, get either of the forces. Our opposite, that is where the angle is facing, becomes FP, right? So sine is equal to opposite over the hypotenuse, which is always longest side, okay? And so in this case, we have sine theta, okay, which is equal our FP over our hypotenuse is W, right? And so we can have this to be, if we cross multiply, okay, we can get our parallel force from here. So this is FP equal W sine theta, okay? Okay, and you can see that we've been able to get our parallel force using this approach, alright? Now let's see how we can get our perpendicular force as the normal force, okay, using the same approach, alright? Okay, now from our SOHCAHTOA, okay, if we decide to use cos theta here, okay, cos theta now is, let us adjacent, alright, over hypotenuse. Let's make references. Now from this triangle, what do we see? Our adjacent becomes Fn. So we have this to be is equal cos theta Fn over W. Alright? So we have, to get our normal force, we have Fn equal W cos theta. And we've been able to get our normal force. Alright? And so we can say that the equation for the parallel components now is given as FP equal W sine theta. And you know that W is equals mg, right? So we can rewrite this as, therefore, Fp equals mg sine theta. While that for the perpendicular component is given as, Fn equal mg, which is W cos theta. Alright? So with this we can get our normal force and our parallel force. Now, in the absence of friction and other forces like the applied force, the acceleration of the object can be determined via an equation involving the parallel component and the Newton's second law. Now it is written as mg, which is our parallel component, mg sine theta equal ma from the Newton's second law. And when you divide both sides by m, you get g sine theta equal a. Alright, so therefore we have a to be equal g sine theta. Now we use the value of the parallel component since it is the reason for the acceleration in the first place. Now, with what we've said so far, we have been able to have a little knowledge on motion of objects in an inclined plane. And so if you have any questions so far on what we have done on this lesson, kindly drop your questions in the comment section below.